All right, here is the key for the third lesson. Homework. Find the points of inflection and examine the concavity of the function. Well, we discovered in previous class that the second derivative will, its signs, the signs of the second derivative, will tell me if the original function is increasing or decreasing. So I would essentially do what I've done for the first derivatives. I'm going to find out when our second derivative could possibly change signs. That's when it's 0 or undefined. For most of these examples, we don't have to worry about the undefined part because we don't have a denominator. I get x equals 0. I will now, on my number line, throw 0 down. This is now the signs of f double prime. And this is telling me the concavity of f. Okay, so let's see. I plug in 1. It's negative 12 times 1. That's going to be a negative. If I plug in negative 1, negative 12 times negative 1, that's going to be a positive. Now, what I write down here is not like going up, going down, because this is the sign of the second derivative. This tells me that the original function is concave up and concave down. So that means x equals 0 is a point of inflection. I'll write POI. All right, let's see this guy. I get 4x cubed minus 3. We're going to examine the concavity, so we're going to go and analyze the signs of my second derivative. I get 12x squared. Set that equal to 0, I get 0. But in this situation, I see that I'll have a function that kind of really flattens out, and I'll have a point of no concavity, but we're going to be going from concave up to concave up because the signs of the second derivative are positive and positive. Not a point of inflection. So it's very, very important to make sure we do this sign analysis. Don't just take the second derivative, set it equal to 0. The rest of them are the same situation. Forgot to say, or undefined over here. Second derivative, see where it could possibly change signs. Step 3, sign analysis of f double prime. If I plug in 4, 8 minus 6 is positive. If I plug in 0, negative 6, negative. Since f double prime is negative, f is concave down. Since f double prime is positive, f is concave up. X equals 3 is a point of inflection. That's negative 1/6. Take the first derivative, I get negative 2/3 x cubed plus 3x squared. Second derivative will be negative 2x squared plus 6x. Cool. Factor out a negative 2x. I'll get x minus 3. Don't worry about the undefined part. But now I have 2 possible points of inflection. I know they're going to be points of inflection because there's no like multiplicity of 2. So there's no even power, which will make things bounce off. So we will have points of inflection, but let's make sure we examine the concavity and know when f is concave up or concave down. I like to start over here, like 4. That's a positive, but that's a negative. So that's a negative. Plug in 1, negative, negative. Plug in negative 1. This will be a positive. This will be a negative. All right, so that since f double prime is negative, f is concave down. Since f double prime is positive, f is concave up. is concave down. So both 0 and 3 are points of inflection, and that's the concavity of my original function. I factor out 12 here. 6. That. Don't have to worry about the undefined. There's no denominator. All right, I get -2 and 3 as possible points of inflection. Let's look at the signs of the second derivative. Plugging in 4, positive, positive, positive. Plugging in 0, positive, negative, positive. Plugging in -3, positive, negative, negative, positive, negative, negative, positive. F is concave up, then concave down, then concave up. So both of these are points of inflection, and this is the concavity. Okay. So the derivative, I get -1/4 x to the 4th. Minus 1/2 x squared. Derivative again. -x cubed minus x squared. Okay. I'm going to pull out a minus x squared so that I get x plus 1. Yep. Don't have to worry about this, just the 0. Now, careful with this -x squared. Yes, a value plugged in to x squared would be positive, but this would be like your value being squared and then take the negative of it. So -x squared is always going to be negative. So if I plug in 1, I'd get a negative times a positive, which is a negative. If I plugged in -1/2, this would be a negative always, because it'd be a positive value, but take the opposite of it. -1/2 plus 1 is positive as well. Do not change sign at 0. I can kind of tell because I have x squared, and 0 is like the solution. Its multiplicity is even. -2 would be a negative times a negative, which is a positive. So F is concave up, and concave down, and concave down. X equals -1 is the only point of inflection. 0 is not a point of inflection. All right. Here's my first derivative. Here's my second derivative. Don't have to worry about that. Zero and 3. Zero, 3. Not going to change signs at 0. Confirming, plug in 4, positive. This will be a negative. Positive times negative is negative. Plug in 1, positive, positive. Plug in -1. Positive, because it's a negative 1 squared. 3 minus negative 1, positive. Positive. So that means F is concave up, kind of flattening out completely, concave up, concave down. So x equals 3 is our only point of inflection. This one's fun. I'll have 1/5 x to the 5th minus 1/4 x to the 4th minus 4x cubed plus 3. Okay. I'll have x to the 4th minus x cubed minus 12x squared. Factor out an x squared. X squared minus x minus 12. Gotta go one step further. X minus 4, x plus 3. Don't have to worry about that. I will have 0, 4, and that should be a 3. I don't know why I wrote 4. 0 should be in the middle of 4 negative 3. Okay, cool. I'm not going to change signs at 0. I know that because of the x squared. But let's see the signs. Positive, positive, positive. Positive, negative. If I plug in 1, negative, positive. So it's a negative. Negative 1, positive, negative, positive, positive, negative, positive is a negative. There's my signs not changing. Negative 4, positive, negative, negative. Positive, negative, negative, positive. F is concave up, concave down, concave down, concave up. X equals negative 3 and 4 are points of inflection. X equals 0 is not. Okay, trig functions. Make sure we go to the second derivative, and now we need to solve. Don't have to worry about that. Add a half, divide by negative 1. I get sine x equals negative a half. Think about my unit circle between 0 and 2 pi. When sine's negative a half, that's when my vertical is down a half. That's at the pi over 6's in the third and the fourth quadrants. That's going to be at 7 pi over 6 and 11 pi over 6. Now, we can understand that we've got 0 and 2 pi, but the next solution, if I kept going around, would be, the pi over 6 after 3 pi. 3 pi is 18 pi over 6's, so it would be 19 pi over 6. 19 pi over 6 is bigger than 2 pi. So I can use 2 pi as a test point. And then for 7 pi over 6, if I went the other way around, the next one would be at negative pi over 6. So I could use 0 as well. So sometimes, even though these are like starting points, endpoints, you can use 0, you can use 2 pi. Probably 2 pi is going to be easy to use here. However, between 0 and 7 pi over 6, I could probably easily use pi over 2. So this is important practice to plug in trig values. Like the best one here would be 3 pi over 2. 2 pi as test points. I'm not plugging in numbers. Now, go back to our second derivative. Negative sine x minus a half. Don't remove anything. So let's see. Let's start with 2 pi. Negative sine 2 pi minus a half. Sine of 2 pi is 0 minus a half, negative. 3 pi over 2, negative sine 3 pi over 2 minus a half. Sine of 3 pi over 2 is negative 1. The opposite of negative 1 is positive 1. Positive 1 minus a half, positive. Pi over 2. Sine of pi over 2 is 1. Take the opposite, negative 1 minus a half, negative 3 halves. So these are the signs of f double prime. This is the concavity of f. We are concave down until 7 pi over 6, concave up until 11 pi over 6. I don't know why I'm drawing that. Why am I doing that? Concave down, concave up, concave down. And, I haven't graphed anything yet, so I might as well do this as the first one just to see our handiwork. Sine x minus 1/4 x squared. Let's look at the concavity. Sine x minus 1/4 x squared. Okay. I might have to adjust things, but watch. I see from 0 until about here, I'm concave down. Now, let's find that value. I think it's at 7 pi over 6. And like right around here, I can see I switch concavity. Boom. Concave down to concave up. Now, if I zoom out, we should be able to see another location where I don't think I zoomed out. Zoom out. Okay. I can see concave down and concave up, and then probably right around here, I switched to being concave down. So right around here, I can kind of see concave up to concave down. I think that's at 11 pi over 6. Yep. Concave up to concave down. All right, so there you go. These are both points of inflection, and we just examine the concavity. Let's look at sine x minus cos x. Well, let's get to the second derivative. Be careful with your signs. Okay. When are sine x and cosines opposites, you can even turn this into like a tangent problem. Subtract cosine or add sine divided by 1. You'll get when tangent x equals 1. Either way, you should get pi over 4 and 5 pi over 4. So, looking at pi over 4 and 5 pi over 4, we'll be able to see if our concavity changes. It will. Again, easy values to use that you need to practice using, and you're plugging it into our second derivative, are like the extremes. Pi over 2, pi, between pi over 4 and 5 pi over 4 is pi. 3 pi over 2 if we wanted to. 0 is fine because our next solution would be at negative 7 pi over 4 if we went the other way. No, it'd be negative 3 pi over 4. So, anyways, here we go. 3 pi over 2. Sine of 3 pi over 2 would be negative 1 plus cosine of 3 pi over 2 is 0, negative. Pi. Sine of pi is 0. Cosine of pi is negative. Okay, so this is negative as well. I messed up. The sine of 3 pi over 2 is negative. I'm taking the opposite of that negative. That should be a positive 1. So this is a positive. Whenever I see signs not changing, I always like make sure that I didn't make a mistake, and I almost made a mistake there. 0, sine of 0 is 0, cosine of 0 is 1, so that's a positive. So concavity does change to pi over 4 and 5 pi over 4. So F is concave up, concave down, concave up. Both of these are points of inflection. Okay, different types of questions. Given F prime, question about F. When does F have a point of inflection? When is F concave up? What is very tricky about this problem is that they don't start you off with F. They start you off with F prime, which means you just need to take the derivative once. And when you take the derivative once, we get this. Now, you can try to factor this, and you can, or you can try to solve this by setting x squared equal to 3. We get a root. I know we haven't had a lot of roots and a lot of funky answers, but we need to be comfortable with getting a funky answer. And this is a situation where we do have a funky answer. So if f double prime is 3x squared minus 9, we will have possible points of inflection at negative root 3 and positive root 3. I'd probably leave it in this form. This is our second derivative. Again, we don't have to worry about the undefined part. I'd plug something like a big number in, like I could plug in 5 or 9 or 10, and square it, subtract 3. That's going to be a positive times 3. That's going to stay positive. If I plug in something like 0, it would be 3 times negative 3. So that's a negative 10 squared, 100 minus 3. Positive times 3 stays positive. Okay, so there's my second derivative. That's telling me f is concave up, concave down, concave up. So points of inflection, concave up when x is less than negative root 3, when x is greater than root 3. For this question, you're given the second derivative. Make sure you understand what is given to you, what your questions are about. It asks you about when f has points of inflection. Given the second derivative, we just need to do our sign analysis of the second derivative. I know 0, 3, and 4. Are you done? And you put the free response just on the paper?
For 18, I accidentally marked A. I wanted the answer to be E, so I kind of like wrote E next to it. So
Okay. So let's see, second derivative, plug in 5, positive, positive, positive. Plug in 3.5, positive, positive, negative, but to the 4th power turns into a positive. So positive, positive, positive.
And could I get a pass?
Plug in 2, positive, 2 minus 3, negative, 2 minus 4, negative, but to the 4th power, positive. So positive, negative, positive, negative. Negative 1, positive, negative, positive. So notice, because of the square, I don't change signs at 0. Because of the 4th, I don't change signs at 4. Not because of the 4th, it's because of like 0 squared. And this is 4 minus 4 to the 4th. So f is concave down, really flattening out, concave down. Point of inflection, concave up, really flattening out, concave up. X equals 3 is our only point of inflection. F is concave down. You know, it's interesting how you can answer this. You would say like everywhere less than 3 except for at 0, but sometimes they'll accept just everywhere less than 3, and they'll say that you are concave down at 0, but I don't know, just to be proper, f is concave down, when x is less than 0, and for x is greater than 0 but less than 3, and I'm not including 0 or 3. All right. Now, given graphs of f prime, answering questions about f, but now we are talking about the concavity and the points of inflection of f. What we will find is that if we wanted to translate this, f prime, into a one-dimensional signs of f double prime, the signs of f double prime come from the slopes of f prime. This is important. The slopes of the tangents to f prime, positive, 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 that means the signs of f double prime are positive until 0. Then the slopes of f prime are negative, which means the signs of f double prime are negative after 0. That's telling me f is concave up, then concave down. We have a point of inflection at x equals 0. It's a location of a relative max. We will find that at these relative maxes and mins, we will have points of inflection, including at sharp points. Sharp points shouldn't scare us. And we're concave up. We have to look at the exact signs of things. X is less than 0 will be concave up. Okay, so same deal. Looking at the slopes of f prime will give us the signs of f double prime. Positive slopes until -1. Negative slopes until 1. Positive slopes after 1. F is concave up, then concave down, then concave up. When is f have points of inflection at -1 and then 1? When is f concave down? Between -1 and 1. Okay, same deal. F double prime. Slopes of f prime. Negative slopes, 0. Positive slopes, 0. Negative slopes, 0. Positive slopes. You'd also think about like decreasing, increasing, decreasing. If you're decreasing, your derivative sign is negative. So negative until -2, positive until 0, negative until 2, positive after 2. F has points of inflection at -2, 0, and 2. F is concave up between -2 and 0, and from 2 to infinity. You can also write this using interval notation. I go back and forth. You need to be prepared to go do either. Oh, look at this guy. Don't be afraid of this. It'll be okay. Undefined points are where one could possibly change sign. So I need to worry about this point at 1. Now, why am I putting -1? I have no idea. Let's just look at slopes. Let's just before we throw anything down, let's just look at slopes. Negative tangent slopes, undefined. This is an important point. I'm going to put it undefined. But then I go negative tangent slopes. So 1, 2, and then positive tangent slopes after 2. We only have a point of inflection at 2, and we are only concave up for x is bigger than 2, or from 2 into infinity. Now, if we thought about like how this could be a sharp point, we could think about the graph of f. And this is what we'll be doing next class, is we're going to be sketching f given f prime. We're going to be increasing concave down until -2, and then decreasing concave down until 1. So increasing to decreasing, concave down the entire time until 1. Boom. Okay, we're going to pretend this is at -1, this is at 1. Then at 1, we shoot, and since f prime is positive, we're going to be increasing, but we're also concave down. We'll end up having a sharp point. Then I'm going to flatten out at 2, change my concavity, concave up, like that. So that would be like what the graph of f looks like. That's what we'll have to do next class, is put it all together. Okay, be careful. Pay attention. I'm given the graph of f double prime. When does f have points of inflection? When does f concave up? Think about what you have. You have f double prime. If you're doing a sign analysis of f double prime, you would say, oh, negative values, positive values, negative values. I don't look at the slopes in this situation. I'm not given f prime. I'm given the graph of f double prime. We have negative values until -3. We have positive values all the way to 2, and then we have negative values after 2. So points of inflection for f are at -3 and 2. When is f concave up? Between -3 and 2. Not the same as when you're given f prime. So be careful. Same deal here. I'm given f double prime. Well, if I was looking at the signs of f double prime, negative values underneath the x-axis, positive values above the x-axis. Negative until -2, positive until 0, negative until 2, positive after that. Where do we have points of inflection? At -2, 0, and 2. When are we concave down? X is less than -2. X is between 0 and 2. Oh, look, I'm given the graph of f. When does f have a point of inflection? Well, now I'm just looking at the shape of f. I can see we go from concave up to concave down at approximately this location, x equals 1. That's a point of inflection. When is f double prime positive? This is an easy question to do if you translate this into behavior of f. If a second derivative is positive, f is concave up. When are we concave up? For all x is less than 1. I can see I'm concave up. That's the shape of f. Okay, so we can give you a lot of stuff with these problems and ask you. So again, this is f. Looks like we're concave up. We switch to concave down here. We switch to concave up here. So -2 and 0. It looks like we go concave up to concave down to concave up. When is the second derivative negative? I'm going to change this question to a translation as when is f concave down? We are concave down from -2 to 0. Right here we are concave down. Okay? So lots of different ways to ask the same questions given different things. Make sure we've understood what you should be looking at when you're given the graph of f, when you're given the graph of f double prime, when you're given the graph of f prime. Okay? Thank you.